I'm really glad that I'm coming after you, because basically I have the method to answer all the questions you couldn't with your method. So that's basically quite nice. So today I would like to talk about a new provenancing tool, the non-invasive portable laser ablation sampling for subsequent trace element and multi-isotope analysis. So this method was developed to reconstruct pre-colonial Caribbean exchange and mobility networks in the Circum Caribbean, because we know that high pressure metamorphic rocks have been used by the Amerindians to produce tools like cells, but also a lot of beads and pendants. A material that was highly valued was jadeite. And we know that jadeite only crops out in Guatemala, Cuba, and the Dominican Republic. So therefore we know that these artifacts have been exchanged and traded over very long distances. And by geochemically fingerprinting those artifacts and comparing them to the source rocks, we are able to contribute to better understand how these former societies operated and were organized. But even if we are allowed to physically examine these artifacts by private or public institutions, most of the time we are not allowed to transport these artifacts and we are not allowed to perform sampling. So therefore, analytical devices have to be portable and they have to be in general non-destructive. So common portable methods like portable XRF, which is non-invasive, and portable laser-induced breakdown spectroscopy, which is minimal invasive, have their limitations. First of all, due to the low limit of detections, they only detect some major elements, light elements, major elements they cannot detect as well, especially portable XRF. And they only detect some of the trace elements. So for example, they do not detect any rare earth elements, which are really important for provenance studies. Then secondly, they need thorough calibration with matrix matched standards. They have a very poor analytical accuracy and precision, and of course they are not able to detect any isotope compositions. So therefore they are most of the time not suited enough to provenance artifacts, because they are not able to discriminate between the sources. Especially in the Caribbean, the jadeites, they are outcropping really close, they are in the same geological setting, so we really have to look for small differences which you cannot detect with those methods. So that is why I would like to present a new method that allows us to sample these precious objects in a macroscopically non-destructive way and perform high precision multi-isotope and trace element analysis afterwards. So this is a picture of the assembled portable laser ablation device, which is a prototype generated at ETH Zurich. Only 2 devices exist worldwide. We have one at the Freie Universität in Amsterdam, and ETH Zurich has one. It consists of an air-cooled dye-pump solid-state laser operating in the green light, so 532 nanometer. Attached you have an optical fiber that leads to a laser ablation module. We are having an open ablation cell which has a tubing connection to a sample holder. The sample holder features a membrane pump and a sample wheel which has space for 6 filters. So how does it work? We put an artifact below and we are ablating the material with the laser. The ablated material will then get sucked in by an ambient airstream which is generated by that pump through that tubing connection onto one of those filters. So in general, one filter consists of one sample, one artifact. The filter is then stored in cleaned centrifuge tubes, which we then transport back to our clean lab for analysis at the Freie Universität in Amsterdam. I also would like to mention that we can also use this laser ablation module handheld, and then we are independent of size and shape of the object, and we can basically sample everything. Yeah. This is a simplified sketch of the optical pathway of the laser beam through the laser ablation module. So the laser beam is entering via the optical fiber. gets reflected by a mirror, then the laser light gets collimated by a first lens and later focused on the sample surface by a second lens. The sample surface is illuminated with an LED ring, and to have full control about where we are on our sample and what we are sampling, we have a CCD camera attached on top. So this is a picture of the device in action. We went to Copenhagen at the National Museum of Denmark to sample artifacts from the Virgin Islands, nephrite and jadeite artifacts. Here you have a view of the CCD camera, which is basically 1 square millimeter. The white light is a reflection of the pulse of the laser. I really would like to highlight that the damage that we are causing is neglectable. You cannot find the spots with the naked eye, even with a hand lens. You have to search for it. The geometry and of the pits and the volume taken strongly depends on the optical fiber that we are using. We can use a normal optical fiber, which will result in width and depth of the crater of 100 micrometer to 130. If we take a tapered optical fiber, one ablation pit will have roughly 50 to 70 micrometer in width and depth, so this is a 20th of a millimeter. So this is taken with a tapered optical fiber in a half Swiss franc. You see the halo around. This is just debris which can be easily rubbed away, then you don't see it anymore. And this is an ablation pit taken with a tapered optical fiber in a natural jadeite rock. The diameter is 50 micrometers, so again a 20th of a millimeter, sorry. Depending on the material itself and on the concentration of the element of interest, and also to get a representative sample, we might need several ablation pits. So for jadeite objects, currently we need 20 because we are interested in strontium and neodymium isotopes, and neodymium is really low concentrated in those jadeite artifacts. Nevertheless, this scale is 1 millimeter, and you see all these 20 ablations are within 1 square millimeter. So it's basically here, and this is 2 millimeter. Unfortunately, we are not able to determine exactly the absolute concentration of trace elements in ppm because we are unable to exactly weigh in the volume that we are taking. This is a requirement to determine the absolute concentrations. But nevertheless, and what is much more important, is we are able to determine precise trace element ratios, which are much more suitable for provenancing artifacts. So we tested the reproducibility of these trace element ratios by sampling a BHVO2 glass standard. This is a basalt glass basically, which is well known, well studied. And what you see on those two diagrams is basically the dashed line is the true value of this basalt standard of two databases, one from the GeoRem database and one from the USGS Geological Survey. The gray shaded area is basically the propagating error of this ratio for the true value, and you see that our data is basically in perfect agreement when we sample with the laser, with the data from literature. I mean, for the GeoRem database, it's even better. We are exactly on that value. Neodymium, strontium, and also lead isotopes are measured by thermal ionization mass spectrometry. The method was also further developed because we wanted to take advantage in the latest breakthrough in mass spectrometry, which basically allows us to analyze really small quantities in a high precision, I would say. So currently we need 2 nanogram of strontium, we need 400 picogram of lead and 10 picogram of neodymium to perform a precise analysis. The only problem is contamination, blank issues. Otherwise, analytically, it's all not a problem. So this modification that has happened, which was the major breakthrough, is a modification in the Faraday detection system, especially in amplifier housing. So this is a simplified sketch of our Faraday detection system. An ion current is hitting the Faraday cup, and then this ion current gets magnified and converted to an output voltage by an amplifier and a resistor, and this is then something we can measure. So normally, if we are having big samples, we would equip our amplifiers with 10 to the 11 ohm resistors. But together with the company Thermo Fisher Scientific, we tested the use of prototype 10 to the 13 ohm resistors. And the result was that for small samples, the output voltage is increasing by a factor of 100, whereas the background noise is only increasing by a factor of 10. So therefore, the signal-to-noise ratio is increasing by a factor of 10, and this is crucial. And this is really nice visible in this diagram, where you see the 86 strontium ratio for a 3 millivolt beam, which is a very small sample of a well-known strontium standard, when measured with the 10 to the 11, 10 to the 12, and 10 to the 13 ohm resistors. This long gray line is basically the long-term average of a big aliquot measured with this machine. And you see that not only the internal precision is improving by a factor of 5, also the external reproducibility is increasing by a factor of 9. So we also wanted to test the reproducibility of the isotopes, and therefore we sampled again this basalt glass standard. What you see in the upper diagram is the reproducibility for the 87-86 strontium ratio. The dotted line gives you the true value from literature, and the diamonds, each diamond is basically 10 ablations. So what you see is, if we have for one sample 10 ablations of this basalt glass, our values are in perfect agreement with the true value. But we also wanted to test our limitations. How much material do we need to sample? What are our limitations? So we decided to do also a test where one sample only has 5 ablations. And what you see, the data is scattering, it's all over the place. So there basically, we didn't overcome the contamination. We didn't sample enough material to get a reproducible result. We did the same for neodymium. This is the 143, 144 neodymium. Again, the true value is the dotted line, and you can see that all our data is in perfect agreement. We did that as well for a natural jadeite rock. I already told you we need 20 ablations because neodymium is so low concentrated. Again, the upper diagram, the strontium isotope reproducibility. The dotted line is the true value, and you see that more or less most of our values are in agreement with the value from literature, but we are having these 5 samples that have elevated values. So what can that be? Either that's a contamination problem, or secondly, that's the heterogeneity of the natural rock itself. So we have to look into that in more detail. So this is something we are still working on it. But again, for neodymium, we have really nice reproducible data, which fits perfect to the value from literature. So basically, our data showed that we are not having any laser-induced isotopic mass fractionation, but also the trace element showed that we don't have elemental fractionation. During the sampling, we are not possible to determine trace element concentrations in ppm of the material itself, but what is much more important is that we are able to determine accurate trace element ratios. You already saw that the reproducibility for the neodymium isotope composition is really, really good. The reproducibility for the strontium is good to fair. So the problem is here the strontium blank. Strontium is everywhere in the environment. You can easily bring it in by dust during sampling, labware, reagents. But we know our contamination. We know the contamination. We know the quantity of our contamination, and we know the isotopic composition of our contamination, and therefore we are able to perform precise blank corrections if needed. And in the future we will work on lowering this contamination issue, for example, by creating a laminar flow wood, like a box around it. And now this is brand new. We already did that, so this is our new portable clean unit, which we can fold together. It has a fan attached on top, so it constantly blows in air, which gives us a slight overpressure, so that we do not suck in any dust. So to conclude, we validated the minimal invasive multiple isotope analysis. It has a huge potential for applications in art and archaeology. It already has been applied and will be applied to all different kinds of materials, glass, ceramics, metals, and rocks, also paintings, pigments. And the take-home message of the day is a combination of isotopes and trace elements is a very powerful tool in provenancing. Thanks for your attention.